In this lecture, we're going to cover the jury test where we've got an unknown Kp value. So the contents, I'm going to give you an initial introduction and motivation as to why we're interested in looking at this. I've got an example, and I'll move then on to the summary and next steps. So after this lecture, you should be able to further understand the importance of stability for a closed loop control system, and understand that the use of the jury test can be used to determine the proportional control gain range to give a stable closed loop control system. As I said in the previous video, for a given Kp value, your poles will move outside of the unit circle. And what we can see here is a root locus plot. This is what we're going to look at in the next lecture. But if you're looking at you can see here your Z plane, your unit circle. Here are your open loop poles, and you've also got a 0 here. So as you increase the proportional control gain, what's happening is the pole locations are changing. So in this particular case, the poles here, this one's moving this way, this one's moving this way, then they break away and move like this, until eventually they end up here on the unit circle. So it's kind of a marginally stable system. Then what will happen is the poles will move outside the unit circle. You can see here, in this particular case, in this pole here, and obviously you get an equal 1 here because the Z plane is symmetrical with that here. And what you can see here is got a system response, and it's unstable because the system response is growing. So here you've got a value of Kp is equal to 0, so there's no proportional controlling because these are my open loop poles. So these are my open loop poles. You can actually see though, for this particular case where the open loop pole here is, the pole's actually outside the unit circle, and then it becomes inside the unit circle, and then moves up, and then eventually comes outside the unit circle. This isn't really actually the best example because ideally you want your open loop poles to be within the unit circle. But what we're going to do anyway is for the example we'll look at the poles, the open loop poles will be within the unit circle, and for a given Kp value here, the poles will leave the unit circle. So as I said, the jury test can be used to determine that range. And just to be aware that in practice, the proportional control gain value is actually limited. You can't just increase your proportional control gain. So in terms of an example here, what I've got is the characteristic equation here of a closed loop control system. So just recall that the characteristic equation of a closed loop control system is just the denominator equal to 0, where Kp is the controller gain and Kp must be greater than 0. Just remember that. So what we need to do is determine the range of Kp for which the system is stable. So the coefficients for the jury table are given by here. So you can see A0 is 1, okay, A0 here, A1 is minus 1.5, A2 is Kp plus 1, and A3 is minus 0.25. Using this rule that we used in the previous lecture, so n is equal to 3, therefore 2 times 3, 6, take away 3, hence we need to use 3 rows on the jury table. And if at any point you're struggling to understand what I'm talking about here, please watch the previous video where I explain this in a little bit more detail. So let's go through the first 3 necessary and sufficient conditions. So condition 1, the absolute value of an, so the absolute value of an, in this case an is minus 2.5. So the absolute value of an is 0.25. That must be less than A0. And in this case, A0 is 1, and hence the first condition is satisfied. Now if we're looking at the second condition, here you can see what we need to do is replace all the z's with 1, as you can see we've done. And for this condition to be satisfied, the product of all that, well, this adding and subtracting this, must be greater than 0. And if you were to look at this, so 1 take away 1.5, so that's going to be minus 0.5, minus 0.5, take away 0.25, so minus 0.75, plus Kp plus 1, because we've got the 1 there, and say for example Kp was 0. Well, something very, very small, the value there is whatever Kp, because Kp's got to be greater than 0, is always going to be above 0. Hence the second condition is satisfied. Condition 3, because we have obviously an n order, look again at the previous lecture if you're struggling as to why that is the case, because the order here is now it's a third order as you can see here, third order. So when we replace all the z's to -1 that you can see I've done here, and when you simplify that, the value of that must be less than 0. So if I'm looking at this, I've got -1, -1.25, minus kp plus 1, minus 0.25. So if you think about that, for whatever value of kp, because you know there's going to be greater than 0, it's always going to be a neg. The product of that is always going to be a negative, and hence it's always going to be less than 0. So that condition therefore is satisfied. So the first three conditions are satisfied. Then what we have to do for the fourth condition is to use the, as you recall, previous lecture, equation 3.3, where we use this. So if we use this, and as you can see, because the obviously third order table is a lot smaller, a lot nicer. So using equation 3, so bn minus 1, so if we just initially look here, bn minus 1 where n is 3, so b3 taking 1, b2, so effectively k is 2. Then if we look at this equation, so a3 is effectively minus 0.25, a0 is 1, okay, so there you can see that there, a3 minus 1 minus k where k is 2, so that's going to be b0, so a0, so that's going to effectively be 1, it's just the same value over here, and a2 plus 1 is going to be a3, which again is going to be the same value that we just put here, and hence you can see that there. Now if we just take the determinant, so this here multiply by this, take away this, multiply by this, that's the values we get, and that's the final solution for B2. And you can see there I've added it into the table. And then I've undertaken exactly the same calculations for B1 and B0. Obviously the only difference being that K is 1, K is 0 in these cases, and hence the values that you use for these and these change. So what you'll notice on these ones is now, because what we've got is effectively k plus 1 in the table here, you'll see that the determinant here in this case is 0.25 multiplied by kp plus 1, take away 1 multiplied by 1.5, and hence you end up with this. And then finally if you look at that, you'll end up with this here. So that there is obviously you've still got kp as a variable, and then you'll see on the next one for B0 exactly the same, you end up with a kp variable. Right, so then we've got that. So then we've got those terms. You can see I've populated them into the table, and what I'm now going to do is condition 4. So if you remember condition 4, because we've only got 3 rows, we only need to use the first equation. So bn minus 1 must be greater than b0. So bn minus 1, the absolute value of that is 1.09375, as you can see there, and that must be greater than b0. So b0 is, here you can see 0.375, take away kp plus 1. So if I'm looking at this equation here, what I'm thinking is, okay, well, first of all, 0.375 take away 1, and first of all we're going to do that, and hence I end up with this. And then I'm going to look at and think, well, what value of kp is going to make this equation here equal to this equation, and the value would be 0.3125. So we had that there as 0.3125. That there would effectively be would be equal to each other. Therefore, because obviously I want this term here actually to be greater, to be less than this here. So hence, what my kp value is going to be is less than that value. So for this condition to be satisfied, this term here must be greater than this term. If I've just worked out what kp needs to be to equal them, then obviously this here actually needs to be less, and hence that I'm interested in values of less than 0.3125. And hence k needs to be less than 0.3125. So for all criteria satisfied for this particular range, so from kp is greater than 0, we knew that already, and less than 0.3125. if we had a KP value of greater than 0.3125, so if we look back at the unit circle, I'm not going to be able to obviously draw exactly where the poles are because I haven't looked at this. You can look at the root locus in MATLAB, but say for example we had poles here, pair of complex poles, KP value here would put me on the unit circle, and the KP value would be 0.3125. Any value greater than that and the poles would move outside here. Any greater value less than that, the poles would be inside the unit circle, hence a stable system. So we're going to talk a little bit more about that in the next lecture when we look at root locus. So in summary, the importance of stability for a closed loop control system have been further detailed, and we've undertaken the steps to use the Jory test to effectively determine the range of KP values to keep the poles within the unit circle, and hence keep the system stable. So as I said, in the next lecture we're going to look at using the rules of root locus to effectively determine the path of the pole location subject to increasing the proportional control gain, which is effectively this plot that I showed you at the very beginning. So thank you for listening. If you have any questions, please drop me an email.